Hey, what's happening, everyone? Welcome to another episode of HPC in the Cloud. I'm Joe Schoonover from Fluid Numerics, and today we're going to be talking about how to connect your Paraview client on your local workstation to an auto-scaling HPC cluster on Google Cloud. We will be picking up from where we left off last week when we ran OpenFOAM simulations using the same solution, but I'll try to catch a lot of you up to speed. So let's just go ahead and get started. Go ahead and head on over to console.cloud.google.com. Once you're there, for those of you who don't already have an HPC cluster on Google Cloud, what you'll want to do is click that Products and Services menu up in the top left, head on down to Marketplace. When that page opens up, just go ahead and type in Fluid Slurm GCP and use that top solution. This will open up the product page, hit launch, and then just go through the configuration form there to get your cluster up and running. Now, basically from where we left off last time, we spun up this cluster and configured it to run OpenFOAM simulations, and today we need to do a couple little changes on the Google Cloud Console side before we get started here. So what you're going to need to do is actually use that Products and Services menu. We're going to set up the firewall rules today so that we can allow a reverse TCP connection from the cluster back to your local workstation on some port other than 22. So if you use that Products and Services menu, scroll down until you get down to Networking. You click on VPC Network, and underneath that sub-menu there, you'll see Firewall. Okay. On the top there, go ahead and click Create Firewall Rules. Let's give it a name. You could just call it PV Server SSH Tunnel would be just fine. Just something representative of what we're doing. Essentially, what we just need to have is a TCP port open for the PV server to reach your client from the cloud. On the network there, if you're just using default networking, you can leave that as it is. If you scroll down underneath the targets, you want to change that from specified target tags to all instances in the network for today. And on the source IP ranges, although you can basically allow anything to connect over that port, we highly recommend you just do a quick Google search, type in what is my IP address, get your IPv4 IP address and enter that in here for the source IP ranges so that only your system or your gateway from your office or your home is allowed to connect to that port. Once you enter that in, down below under the protocols and ports, click that TCP button there, and then today I'm just going to walk you through how to just use port 11,000. If you have a lot of users who are going to be using the Paraview server, from their Paraview client, you might put in a range of ports here, but just go ahead and enter in 11,000, and when you're done, hit create. Now, I've already created one for myself, so I'm not going to do that here, but you'll need to do that to get started. Now, the other spot, if you're just joining today, and this is your first time spinning up the cluster, you need to go into the Identity and Access Management panel and give yourself two permissions. You really need the Compute OS admin login role and service account user. So to do that, from the Products and Services menu, you go down to IAM, click on Add, put your email address in the new members entry there, and then on the roles, just look for Compute OS admin login, and then you'll also want service account user. This will allow you to use third-party SSH tools like OpenSSH to connect to the cluster, and that really should be it. So from here, what we want to do is hop into our cluster to configure the partition to use a Paraview image that we've created for y'all. It's publicly available on Google Cloud. So the way we're going to do that is up on the top right, I'm going to click on this Activate Cloud Shell button here, which is going to bring up a terminal window in my console. And from this terminal window, we're going to SSH into our controller node here because we're messing with the partitions. You need to be on the controller whenever you're configuring your compute partitions. So we'll click copy to clipboard there to get the external IP address, and let's go ahead and hop in. So I'll catch up to speed real quick with what we had left off with from last week. So last week we had run the Aerofoil NACA 012 demo, which gave us a bunch of OpenFOAM output, and we downloaded this Fluid Slurm GCP custom image bakery. This has some resources in it that will be useful for you today, particularly the Paraview GCP PVSC file, and a script that will basically go through submitting a batch job on your behalf. Where we're going to get started though right now is just configuring those partitions so that we can run Paraview. So go ahead and go root. is we're going to be running cluster services, and if you remember, that tool does require root access to be able to run it. Let's open up that config.yaml, and we're going to scroll up. Let me get the line numbering on here for you. Basically what we're going to do is create another partition from where we left off. So last time we had created an OpenFOAM partition, and that had the OpenFOAM GCP image in it. You can see that down here on line 31. What we're going to do is copy this partition block. We're going to paste it below, modify it so that we can use that to create our Paraview partition. So starting from line 22, let's see, that goes down to 43, so that's 21 lines. We'll copy and we'll paste below. All right, now in this partition, I want to change the image. Instead of OpenFOAM GCP, we're going to change this to Paraview GCP. And then for the name of those compute nodes, I'll call them Paraview USW2C, because we're launching these in US West 2. You can call them whatever you like, of course. And then on the name of the partition, I don't want to name that partition OpenFOAM. I want to name this Paraview. So basically, we'll end up with two partitions, one for OpenFOAM, one for Paraview. And that's how we'll be able to segment our workloads for various purposes. So that's about it there. The other section we want to now add, make some changes to, is on the Slurm account. So before we had set up Slurm accounts to use, to allow myself really just to use the OpenFOAM partition. I now want to add the Paraview partition in here. And then we're going to go through the two steps of running with cluster services to update the partitions first, and then we'll update the Slurm accounts. So we'll run cluster services, update partitions, config equals config.yaml, and we're going to give it that preview flag just so we can double check our work before we make the changes. So we got the name of the partition is Paraview. Let's see here, the name of the compute instances are Paraview USW2C, and then the image is showing up with Paraview GCP. So we should be good to go. Let's go ahead and rerun that command and just remove that preview flag. Once this is done, we'll basically double check our work here by running sinfo to make sure we now have two compute partitions, and indeed we do. We have OpenFOAM and we have a Paraview partition, and you can see the node list for each of those. So now what we want to do is update the Slurm account so that we can submit jobs to both the OpenFOAM partition and the Paraview partition. So we'll run cluster services, update Slurm accounts. Again, give it that config file that we have in our local directory, and run preview. Okay, now this looks good. We're basically updating the first Slurm account. We're adding another partition to it, the Paraview partition. So basically run that command with the preview flag removed. Now for those of you who are just catching up today, if you're wondering how we got that config file to begin with, if you just run cluster services list all, that will give you a full listing of the current cluster configuration, and that should give you your starting point if you pipe that to a file like this. That should give you your starting point to be able to customize your cluster. Okay, so now that we've configured the partitions, we've configured the Slurm accounting, what we need to do now is actually go into the login node and turn on the gateway ports feature of the SSH daemon. So that we can basically do a reverse connection from a compute node through the login node and back to your Paraview client. So let's go ahead and log out of the controller, copy that login node IP address, and go ahead and SSH in. Okay. Make sure you're in that login node. You can see in the shell here, you'll see the word login on the name of the instance. So let's go ahead and clear the screen here so we can see what we're doing. We're going to go root because we do need to modify a file underneath etc/ssh. So if you open up etc/ssh in your favorite text editor, I like Vim. I know some of you guys like Emacs or Nano. All of those are available on this system. Go ahead and open that up, and then you're going to look for the keyword gateway ports. Okay, it should be commented out when you first get in here. Go ahead and uncomment that line and change that no to a yes. And then you'll use systemctl to restart SSHD. So that's really it on that side of it. Now what we got to do is there's a couple steps here to set up the Paraview job submission script. I'm going to walk you through one way of doing it. So we basically provided these job submission scripts in this Fluid Slurm GCP custom image bakery. Now, if you missed this last week, if you check out our GitHub page under the Fluid Numerics organization, you'll see a repository called Fluid Slurm GCP Custom Image Bakery. And this has a lot of resources for just getting you started with baking your own compute nodes, compute node images that work with our cluster. But underneath the examples, in the Paraview directory specifically, we have a Paraview server connection file that you're going to use today. And we also have this submit paraview.sh script that's all part of this system to allow you to connect your client to compute nodes. So if you don't have that, go ahead and clone that onto your cluster. And if you check, again, what we're going to do here is we're going to create a directory underneath apps. We'll call it share. Okay. And then what I want to do is copy from the Fluid Slurm GCP custom image bakery repository underneath the examples, underneath Paraview, the submit paraview.sh. We want to move that on down to app share. Okay. Once you've done that, you also will need to chmod that so that you can make this this script executable. So you can do chmod 755 is just fine. And then we'll do apps share submit paraview.sh. So if you were to do a long ls on that apps share, okay, you should have an executable bit for yourself. Well, I guess for groups and others as well, since it's technically owned by root. So if that all looks good from your side, what we're going to do now is hop onto your local workstation. We're going to copy down that Paraview gcp.pvsc file onto your local workstation, and we're going to spin up Paraview to try to connect to this system. Okay, so on my local workstation here, basically what I need to do first actually is grab that IP address for that login node, because we're going to SCP down that Paraview file. So do SCP, well, I'm getting ahead of myself. Let's make a directory to stick this PVSC file. So let's call it Paraview PVSC. And then we'll do our SCP, your username at your cluster, login node IP address. This is going to be Fluid Slurm GCP custom image bakery, examples, Paraview, and then Paraview GCP.pvsc. Okay, we're going to stick that file inside of the Paraview PVSC directory we just created. Okay, so this is just an XML file that Paraview will use to help you walk through an easy way to connect your client to the cloud. So go ahead and start Paraview. Highly recommend that you're starting with at least 5.8 here, since that's the same version we have installed on that Paraview GCP compute image. If you're working with an earlier version, you may run into some trouble, but definitely just go ahead. If it's really easy, just hop over to that Paraview website and go through the downloads there and get the latest version. Okay, so the first thing I'm going to recommend you do is, if you look up on the top there, there's on the toolbar, just click on View, and then open up that memory inspector on the side. And reason why I recommend this is because you can see right now all I've got is my local workstation, this Meerkat. Basically, what's going to happen here is once we connect to our cloud compute node, we'll see another compute resource show up here with all the compute resources that are available on that node. All right, so to connect to that server, up on the top left there, kind of next to that open file icon, you'll see a connect button there. It looks like two servers with a green light between them. Go ahead and click on that, and you should get a choose server configuration dialog. When you're in there, go ahead and hit load servers. Navigate to that directory you just created. Mine's Paraview PVSC, and then you should see that Paraview GCP.pvsc file. Go ahead and click on that, and then once that's loaded, hit connect. What you need to do here is fill out this form to basically, what's going to happen when you hit connect here is the Paraview client is going to spin up, in this case, xterm, and in that xterm window, it's going to run some commands over SSH automatically for you. What it's going to do is it's going to set up a SSH tunnel over port 11,000 from the login node back to your local workstation. It's also going to run a command to execute this app share submit paraview.sh on your behalf using the rest of these configurations down below, like your Slurm account, the Slurm partition you want to use, the number of MPI ranks, or the number of processes, the amount of memory per MPI task, and the number of hours you want to reserve for. So it's really key here just to get some of this information correct. Make sure you know your SSH username, and you're using the username that's applied on the cluster, not maybe on your local workstation. Let's get that IP address one more time just in case I've got it incorrect here. paste it in. The nice thing is once you fill this out once, all those settings Paraview will remember those settings for this cluster connection, which is pretty cool. Again, make sure that port matches that firewall port that you opened up previously, and then you should be good to go. We'll click OK here, and what you should see is that xterm window open up, and it's going to show you that batch script that it is submitting on your behalf, and then it'll keep track of that job status for you. Now, while this is kind of going on here, let me show you what's actually happening on the cloud side so you can kind of get an idea of what's going on. So we have this thing, it's waiting for the server to connect. If I hit refresh on the cloud console, you now see we have a Paraview node from the Paraview partition. And then down in the terminal here, since I'm still in the login node, I can run SQ, and you'll see that Joe, myself, actually has a job running on Paraview, and it's basically going to deploy on that particular node. So because this node, this is an auto-scaling cluster, these nodes have to be provisioned on the fly. And this process can take anywhere from 30 seconds to like 3 minutes. So while we wait, let me kind of walk you through what we're going to do next here. Because of course, at this point, if all you wanted to know is how to connect to Paraview, this is it. Now, since I said we were picking up from that OpenFOAM simulation we did last week, I just basically wanted to do a very simple schematic or very simple simulation rendering from our NACA 012, the flow past the NACA 012 airfoil. So if you remember what we were doing, is we have the compressible flow solver from OpenFOAM set up to have flow go from left to right across the screen past this airfoil that I'm showing you here. All right, so if we have, let's see, the X and Z directions set up here. So we got X in the left to right, Z up and down. There's an inlet flow on the left side that's uniform. Now, of course, this is not all to scale. That inlet flow is pretty far away from that airfoil. But basically, we've got this kind of scenario set up. And what we want to do in the visualization is set up, basically what I want to show is the pressure that arises on the surface of the airfoil, and then I also want to show some streamlines that depict, what's happening with the flow around that airfoil. So what we'll do is we'll end up putting some seed points for the streamline filter in Paraview in front of that airfoil, okay? And then we'll just have those streamlines be created by integrating forward along the, using the velocity as the tendency for like a particle position to trace out streamlines. And what we should end up seeing is something that, the flow just kind of comes around. I mean, for those of you who've done fluid mechanics, you already know what we should be seeing. So you'll be able to tell right away if something's gone wrong. Of course, we shouldn't have crossing streamlines like that, but I think you get the idea. Okay, so at this point, I think, we're all connected here. You can see now in that memory inspector window, we now have the Paraview USW2C0 node showing up as our server. Nice thing is when I click on the open file window now, I can actually get all the files that are stored up on that cluster. I basically use that file system to pull in data. So I'm going to go into that airfoil NACA 012 example. We'll open the NACA 012.foam file. If you don't have one of those when you ran the simulation last week, you can create an empty file just by running touch whatever.foam. It doesn't matter what the name is. I'm going to go ahead and open it twice because one of them I'm going to use for visualizing the pressure on the airfoil surface, and then we'll use the internal mesh to do the streamline calculation. So on the first one here, let's only do the airfoil down in the mesh regions, and let's uncheck everything except for pressure. Okay, and then on this other one, we're going to uncheck everything except for U, and we're going to leave it on the internal mesh. Now to get our view set up once this actually goes through, now keep in mind what's happening here is when we're actually doing this rendering, basically our client's sending instructions over to PV server. The PV server is actually doing all the heavy lifting, and then the rendered product is sent back to the client. So it's pretty nice. Of course, this is a pretty small data set, so it's really just proof of concept here, but the idea being, of course, if you have a larger data set and you need the extra compute resources, this is a very, very clean way to get that done. So for now, I'm going to go ahead and just hide this internal mesh, and let's zoom in on our airfoil. So here we're just looking at the pressure on the surface of the airfoil that flows going from left to right here. And you can see we get that high pressure on the front where there's like a stagnation point, and the flow is diverted around the airfoil, and the pressure of course, gets low around the top of it where the flow is the fastest. So let's go ahead and configure the Streamlines here. So if you're familiar with Paraview, you probably already know where this is going. For those of you who are not, if you check out up in this top row here, just above the pipeline browser, you'll see what looks like a bluff body diagram with some streamlines around it. Go ahead and click that stream tracer, and that'll add that stream tracer filter down below. What we want to do is we only want to have the streamlines found in the direction of the flow, so we don't want to go forward and backwards. We just want to go forward in the direction of the flow. And in terms of the streamline length, now although the domain is like 150 meters long, the airfoil itself is only a few meters. So I want to back this off to about 3 meters. And then let's pick a point in front of the airfoil. Now the airfoil is essentially placed right about where X is 0 and Y is 0. Roughly. So I had to pre-calculate these just so I could get this right for the live stream. But we'll basically pick the points where we're going to seed the streamline points for the start of the streamlines at minus 0.2 in the X, minus 0.5 in the Y, and then the bottom of that line is going to be 0.1. So you can see we've already got the start of that streamline source. There, and then we're going to pick 0.2 in the X, minus 0.5 in the Y, and then we're going to go to minus 0.1 in the Z. All right, so that sets us up with basically along this line, we're going to evenly divide points along that line and use those as the starting points for the streamlines. I don't need 1,000 points. Let's drop that back down to 20 and hit apply. And so what we should see is those streamlines, kind of like that diagram I showed. This is obviously much nicer, showing the flow being diverted around the airfoil. Now, when we're done simulating, you might want to save the image, of course, or there's a lot more post-processing you do. The point of this exercise was really not to get into the details of post-processing with Paraview, but really to show you that you can connect your Paraview client with the scalable resources of Google Cloud to accomplish your computational fluid dynamics workflows. In this case, I'm just going to go ahead and save this just so I have some nice pictures just to remind myself of this tutorial. Let's call it Google Naka 012. All right, so that's done there. Now when you're done working with your server, so like what you'll see right now if you're on the cluster, if I were to look at that SQ, you'll see that you have a running job right now. But if I go into Paraview and I hit that disconnect button at the top, what'll happen is, one, we'll lose all this data. Okay, so of course you make sure you save your Paraview state or anything like that if you want to come back to your work later. But now what you'll see is up on the cloud, that job has now been canceled on your behalf. And if you remember from previous tutorials, we basically said, when these compute nodes go idle for 5 minutes, those nodes will be taken down automatically for you. So that's really it. That's all I really wanted to show you guys today. I hope you all found this useful. And of course, if you have any questions, feel free to reach out on the chat window here on this live stream, or reach out to us at support@fluidnumerics.com. I'd be happy to connect with y'all. Thanks again for tuning in.